In this video, we'll go over the homework that follows the lecture on the remainder theorem. And as always, I hope that you watched the lecture before attempting the homework. And let's go ahead and jump right into the homework. And the first question is to find the upper bound for the remainder. And we have the function cosine of x. It's a Maclaurin polynomial, so it's centered at 0. And we're trying to estimate cosine of 0.7. And you know cosine of 0.7 is equal to f of 0.7, but f of 0.7 is equal to the polynomial of degree 4 evaluated at 0.7 plus the remainder at 0.7. And the remainder theorem says that the remainder is less than or equal to the following expression. And I'm going to use C as the center. Now, everything is pretty much given to us. We have k equals 4, c equals 0, x is equal to 0.7. The only thing we don't know is m. What is m? M is the upper bound for the k plus 1th derivative. On the interval from the center to the value on which we're estimating. So let's go ahead and find the derivatives of this function. We have the first derivative is negative sine, the second derivative is negative cosine, the third derivative is again negative positive sine, the fourth derivative is cosine, and the fifth derivative is negative sine. So we need to find the maximum of negative sine x on the interval from 0 to 0.7. So let's go ahead and open Desmos. We have sine of x on the interval from 0 to 0.7. And it looks like it's an increasing function, so it reaches its maximum at 0.7. So if we set m to be equal to the sine of 0.7, then that m will be a great choice. Now that we figured out all the ingredients, we can find the upper bound for the remainder. It's going to be sine of 0.7 divided by 4 plus 1 factorial. X is equal to 0.7, c is 0, k is 4. So sine of 0.7 divided by 5 factorial times 0.7 to the power 5. And we got 0.00090. So the answer will be rounded to 6 decimal places. 2. Rounded to 6 decimal places, it will be 0.000902. All right, let's take a look at the next question. Determine the degree. So we have a function. We are dealing with Maclaurin series, so we are centered at 0. And if we're going to estimate 4e to the power 0.21, we're going to plug in 0.21 in here. So it's going to be some polynomial evaluated in 0.21 plus remainder at 0.21. Now by the remainder theorem, this remainder will be less than or equal to m over k plus 1 factorial times x, which is 0.21, minus c to the power k plus 1. And m is the upper bound for the k plus 1 derivative of x on the interval from c to x. So c in this case is 0, it's the center, and x is 0.21. And what we're going to do is we're going to evaluate the we're going to start with derivatives. F of x is equal to 4e to the x, and what's nice about this function is that all derivatives are the same, so we know exactly what the k plus 1 derivative is going to be equal to. And now if we try to maximize it, so if we look at 4e to the power x on the interval from 0 to 0.21, it looks like it reaches its maximum at 0.21. So a good choice for m will be 4 times e to the power 0.21. And now we have all the ingredients, so we need to, what do we want to do? We want the r of k to be less than 0.01, and one way to make sure of that is to make sure that this expression is less than 0.01, which will force r to be less than 0.001. So we set up this inequality. And we need to find the values of k that make this inequality true. So let's use Desmos for that. We're going to create a table of inputs, outputs. Here we have k, here we have 4e to the power 0.21 divided by k plus 1 factorial 0.21 to the power k plus 1. And when k is equal to 0, we get that, so it looks like k is equal to 3. This is when we can satisfy this inequality. So we're going to answer 3. All right, similar problem. The function is 2ln x plus 1. And the center is 0. And I already forgot how we set it up here. So we're trying to estimate it at 0.31. So f of 0.31 can be estimated by pk of 0.31 plus rk at 0.31, and we know that rk is bounded by this. And we actually don't need the absolute values here. We need to find m. M is the upper bound for the k plus 1 derivative. Actually, it's an upper bound. Did I write it correctly here? Yes. It's an upper bound on the interval from the center to the value. And to identify this upper bound, we're going to start differentiating. So the first derivative is 2 over x plus 1. The second derivative is negative 2 over x plus 1 squared. The third derivative is going to be 4 over x plus 1 cubed. And we need to see what's going on here. So let's take a look at the graph. We're going to have, here's our f of x, and here's the absolute value of the first derivative, and we're looking at all of this on the interval from 0 to 0.31, and this is the second derivative, and this is the third derivative. Let's see. This is the fourth derivative. So it looks like it reaches the maximum at 0. That's interesting. So can we express this formula? Can we find the kth derivative somehow? Let me see. What's the pattern here? We have 2 times x plus 1 to the power negative 1. We have 2 times negative 1 x plus 1 to the power negative 2. We have 2 times negative 1 times negative 2 x plus 1 to the power negative 3. So it looks like if this pattern continues, then the nth derivative will be 2 times negative 1 to the power n minus 1. And we're going to have n minus 1 factorial times x plus 1 to the power negative n. And it seems like now we need to find the n plus 1th derivative. So it's going to be, we're just going to add 1 to each appearance of n. And it seems like this is always going to be decreasing function, which achieves its maximum when x is equal to 0. So a good choice of m will be this value, and we're going to put k here instead of n, and we're going to plug in 0 for x. So, and we're going to take the absolute value of that, so it's just going to be 2k factorial, which is a pretty nice pattern to know. And now we can plug everything in to this inequality. We want this to be less than what? What was the problem? I already forgot. 0.01. Right, so this is the inequality that we are trying to solve. So m is now two times k factorial divided by k plus 1 factorial, and we have 0.31 to the power k plus 1. We want all that to be less than 0.01. And let's plug this in. We have 2k factorial over k plus 1, 0.31. And it looks like the first time the inequality is solved is when k is equal to 5. So the answer is k equals 5. All right, so this was what, number 3. Let's do number 4. In number 4, we have a function f of x is equal to square root of x. We center it at 9. And we're using the 4th Taylor polynomial, so we're evaluating square root of 10, so f of 10 is equal to p4 of 10 plus r4 of 10. Now, r4 of 10 is going to be less than m divided by k plus 1, so, but k is 4, so it's going to be 4 plus 1 factorial times 10 minus 9 to the power k plus 1. Again, k is 4. M is the upper bound for the k plus 1 derivative, so we're talking about 5th derivative here. On the interval from the center to the value. And now we need to find the derivative, 5th derivative. So the first derivative is 1/2 x to the power negative 1/2. The second derivative is 1/2 negative 1/2 x to the power negative 3/2. The third derivative is 1/2 negative 1/2 negative 3/2 x to the negative 5/2. The fourth derivative is 1/2 negative 1/2 -3 halves, -5 halves, -7 halves, and the fifth derivative is and we probably want to graph that. So the graph of the fifth derivative is, let's see, what do we have? We have 3 times 5 times 7 in the numerator. 2 to the power 5 in the denominator. X to the power -9 over 2 on the interval from 9 to 10. So it's hard to tell what's going on there. Oh no, now we can see exactly what's going on. The function is decreasing. That means it reaches its maximum at 9, and we choose m to be 3, 5, 7 over 2 to the 5, 9 to the power -9 halves. And now we're ready to plug that value in here and compute this upper bound for the remainder. So we're going to have 3, 5, 7 over 2 to the 5, 9 to the power -9 halves, all divided by 5 factorial and multiplied by 1 to the power 5, which is just 1. So this is 9. All of that is divided by the 5 factorial right over here. So this is our answer. I don't think I need that many periods. 0 point, we have 5 zeros, 1, 3, 8, 9. And the question here is asking to enter the answer at 6 decimals. 0, 0, 0, 0, 0, 0, 1. And it looks like we completed the homework. And if you have any questions, please reach out as soon as possible.